Hi there, welcome to this Elkchemist chemistry video looking at chemical analysis, specifically how we test for the presence of cations, positive ions found in samples of compounds. So, if we want to find out what cations might be found inside an ionic compound, our first line of inquiry would be a flame test, because it gives a very clear visual indication of whether certain ions are present. To carry out a basic flame test, all we need is a piece of nichrome wire loop on the end of a plastic handle. Nichrome is an alloy which is ideal for this experiment because it is both unreactive and has a high melting point. Therefore, it won't interfere with our experiment, and also it will be able to withstand the heat of a roaring Bunsen flame used in our flame test practical. The practical method itself is extremely simple. We take our nichrome wire loop, dampen it with some distilled water, and dip the end of the nichrome wire loop into a solid sample of the ionic compound of interest. We then turn the Bunsen collar to an open collar, hold our sample of our ionic compound on a nichrome wire loop at the top of the inner cone of the Bunsen flame, which is the hottest part of the Bunsen flame, look for the emission of colour, and the experiment is finished. To make sure the nichrome wire is clean, we then dip it into a small amount of hydrochloric acid and then hold that over the roaring Bunsen flame to burn off both the hydrochloric acid and any remaining sample of ionic compound, and then we're ready to do the next test. You may be wondering why heating ionic compounds containing metal ions causes them to emit coloured light. Well, the reason is that electrons around those metal ions in the various shells are being excited. They're absorbing energy, thermal energy from the flame itself, which promotes those electrons, raises those electrons to higher energy states. Now, those electrons will then fall down from those high energy states to their ground states, their original energy levels. In doing so, they must emit the energy they have absorbed, and they emit that energy in the form of wavelengths of light. So each of the various ions shown on this page has a unique emission spectrum. They all emit a unique pattern of various different wavelengths of light, and therefore various different coloured photons of light will be emitted from the heated ionic compound samples. The culmination or coalescing of all those various wavelengths of light usually produces a single distinctive and prominent colour for that particular metal ion when it undergoes this experiment, this flame test experiment. And that's the colour we observe, and that's the colour we're looking for. I'm going to take you through some of the truly stunning flame test colours you might experience. So when lithium Li+ ions are intensely heated, you will see a stunning red flame, crimson, scarlet, deep red. When sodium ions are heated, you will see a bright yellow flame. That's due mainly to a specific wavelength of light being emitted by the sodium ions at the 589 nanometer wavelength. Heating calcium 2+ ions produces a really beautiful orange coloured flame, sometimes described in textbooks as being brick red. Now, strontium 2+ ions when heated can give quite a similar colour to calcium ions to the lay observer, but in reality, if you look really closely, it is slightly more red than the calcium flame. Not as red as lithium, that scarlet colour, but a red-orange flame would correspond with strontium 2+ ions. Now, when copper 2+ ions are heated intensely, you'll see a truly magical blue-green flame, reminiscent of the spell from the Harry Potter franchise, Avada Kedavra, and it is really special to see. Now, potassium K+ ions produce a quite hard to spot lilac flame. Many students describe this as looking more like a peach colour when they do their flame test. But if you add pieces of potassium metal to water in the reactions of alkaline metals with water, you will really see that lilac flame in that reaction. And finally, barium 2+ ions give what is known as an apple green flame. Again, quite hard to spot, so my colour here is sort of a yellow and green mixed together. It's quite a light green colour, but it is most definitely there if you look closely. So hopefully by now you would notice some of the limitations of using flame tests as a way of analysing compounds. The flame colours are quite subjective to the human eye. One person's red could be another person's orange based on their perception of colour. Also, two different elements can have very similar flame tests. On our examples here, calcium 2+ ions and strontium 2+ ions would give reasonably similar flame colours when observed and could confuse the observer. And other factors would be important as well. The lighting in the room would have an effect as well. So you can see that we need a second layer of testing to be sure of some of these observations. And that's what I'm going to move on to in a little while. Okay guys, at this halfway juncture, I just want to say two things. Number one, if you're finding this video useful, please do think about maybe giving it a like, thinking about subscribing to the channel, maybe even ringing the bell to keep notified of my latest content. I try and put out videos on literally a weekly basis. Got a growing library of revision videos for students of all ages, and your support is hugely appreciated and helps motivate me. You can even think about sharing this content with friends who are studying chemistry to help them as well. Number two, if you're finding this flame test idea interesting, please check out the card that will appear in this video, which takes you to one of my experiments where I create something called flaming beakers, which have various colours, and it's really exciting and really shows off some of the colours I'm talking about here incredibly well. So check it out. The second phase of cation testing involves adding sodium hydroxide solution to dissolved samples of our possible cation ionic compound and observing what happens. And it's based on the principles of solubility and precipitation reactions. A precipitation reaction is defined as being a reaction in which an insoluble solid is formed when two solutions are mixed together or when a gas is bubbled into a solution. So we're going to be looking for either the formation of solid insoluble products or not, depending on which cations are present. So when sodium hydroxide solution is added to dissolved samples of group 1 metal ions, such as lithium ions or sodium ions, nothing seems to happen. And that's because group 1 hydroxides are soluble in nature, so you're not going to see any visible change because no precipitation reaction is taking place. So if the solution remains a colourless liquid, then you can be pretty certain you've likely got a group 1 metal ion present. On the other hand, group 2 hydroxides become more insoluble as you ascend group 2 itself. So if we were to add sodium hydroxide solution to, say, magnesium ions or calcium ions, then we'd see a sudden and instantaneous formation of a white solid precipitate, confirming the presence of those group 2 metal ions. I've also included some ionic equations representing those precipitation reactions. For example, magnesium 2+ ions in aqueous solution reacting with 2 hydroxide ions in aqueous solution to form the solid precipitate magnesium hydroxide, Mg(OH2), or calcium 2+ ions aqueous reacting with 2 OH- ions to form calcium hydroxide precipitate solid, Ca (OH)(2). 2 hydroxide ions to every 1 calcium ion because it's a 2+ charge on the calcium ion being balanced out by the -1 times 2 charges of the hydroxide ions. Now, zinc ions and aluminium ions, Zn2+ and Al3+ respectively, have a really interesting precipitation reaction. When you initially add sodium hydroxide solution to a solution of zinc ions or aluminium ions, they appear to form a white precipitate, very similar in appearance to the magnesium ions and calcium ions observation. But there is a difference. If you keep adding more dilute sodium hydroxide on top of that precipitate, excess sodium hydroxide, you'll see that it looks more like a snow globe. It seems as if the precipitate is starting to dissolve and disappear again. And that's exactly what happens. If you add enough sodium hydroxide, it will vanish completely. I'm not actually going to go through the specifics of the reaction taking place there because what's going on is literally complex. i.e. it involves the formation of something called complex ions that I'm not going to talk about in this video, but I might talk about in a future A-level video. So look out for that if you're interested. Now, this final page of precipitation reactions is really nice because this is about the colours. If you add sodium hydroxide solution to copper 2+ ions, what you produce is a bright blue precipitate. And so here's the ionic equation for that reaction. Copper 2+ ions aqueous reacting with two OH- ions aqueous hydroxide ions in aqueous solution to form the solid precipitate, which is blue in colour, Cu open bracket OH close bracket 2 copper hydroxide solid. On the other hand, if you add dilute sodium hydroxide solution to iron 2+ ions, Fe2+ ions, you produce a green precipitate. Kind of looks not dissimilar to moss when you see it up close. And again, here's the ionic equation for that reaction. Fe2+ ions in aqueous solution reacting with two OH- or hydroxide ions in aqueous solution to form the precipitate Fe open brackets OH close brackets 2 iron hydroxide green solid precipitate. And if you add dilute sodium hydroxide solution to Fe3+ or iron 3+ ions, different oxidation state of iron ions, you produce a different coloured precipitate, in this case a red-brown, almost rust-coloured precipitate, but call it red-brown. That is Fe3+ ions in aqueous solution reacting with three OH- ions in aqueous solution to produce the compound Fe open brackets OH close brackets 3 solid precipitate, a different formula to the iron 2 hydroxide. This last example is the joker in the pack, the example they use to catch you out. If you add sodium hydroxide solution to an ammonium ion NH4+ ion solution, there is no precipitate formed. So initially you might be thinking, well, I've got a group 1 metal ion solution, I must do, there's no precipitate formed. But the trick is to then heat that mixture. What will happen is the ammonium ions will react directly with the hydroxide ions present. In doing so, they will produce gaseous ammonia and water. Well, the ammonia is probably not initially gaseous, but the heating will turn it into a gas and water. Now that ammonia gas will leave your test tube or boiling tube, and it's an alkali gas. So if you take some damp red litmus paper and hold it over the gas escaping from your boiling tube while heating your mixture of ammonium ions and hydroxide ions, that ammonia gas being emanated will interact with the red litmus paper, turning it blue, proving that an alkali gas is disseminating from the boiling tube and helping to prove that ammonium ions must have been present because this reaction must have been going on between the acidic ammonium ions and the alkaline OH- hydroxide ions to form specifically an alkaline gas, which is ammonia gas, which is creating the observation of turning the red litmus paper blue. Well, folks, there you have it. That's halfway through our journey of understanding analytical techniques to test for the presence of ions. We've covered cations. I hope you'll join me in the next video where I'll talk about how to test for the presence of anions, which are negative ions. As always, thank you so much for listening to the end. Hugely appreciate it. I hope that was very helpful for you, and I really look forward to talking to you in the next video or in future videos. Take care now. Bye-bye.